For most of human history, one disease killed more people than almost any other on Earth, and nobody knew why. It struck without warning, in waves of shaking fever, and it had a name that told you everything about how little anyone understood it: malaria, from the Italian for bad air. For centuries, doctors were certain they knew the cause, and they were completely wrong. They blamed foul vapors drifting up from swamps and marshes, poisonous air that supposedly seeped into your lungs at night and set off the fever. No insect was ever suspected. The word itself comes from the Italian malaria, literally bad air, coined by Italian physicians describing the fevers that rose from the lowland marshes near Rome. An English visitor named Horace Walpole carried the word home to England in a letter in 1740, and it stuck. This was the miasma theory of disease, the idea that rotting, swampy air itself carried sickness, no living agent required. It explained why marsh dwellers got sick more than mountain dwellers. It just happened to be built on the wrong villain entirely. Ancient physicians had already linked the fevers to marshes centuries earlier. Hippocrates himself wrote about marsh fevers, and Roman writers drained wetlands near their cities specifically to push the sickness away. The connection to swamps was old. The reason for it was invisible to everyone. And yet, remarkably, an actual cure existed centuries before anyone understood the cause. In the Andes, Peruvian communities used the bark of the cinchona tree to treat fevers. Jesuit missionaries carried it to Europe around 1640, where it became the standard malaria treatment for 200 years. In 1820, two French chemists, Pierre Pelletier and Joseph Caventou, isolated the bark's active ingredient and named it quinine. Doctors now had a precise, purified drug that reliably broke malarial fevers. They still had absolutely no idea what quinine was actually curing. By the late 1800s, a new scientific revolution was reshaping medicine entirely: germ theory. Louis Pasteur and Robert Koch had shown that specific, visible microorganisms cause specific diseases. Suddenly, doctors everywhere went hunting for malaria's own hidden germ. In 1879, two Italian researchers, Edwin Klebs and Corrado Tomasi Credelli, announced they'd found it, a rod-shaped bacterium they pulled from marsh soil and named Bacillus malariae. For a few years, this looked like the answer everyone had been chasing. But the bacterium never quite held up. Other scientists struggled to reliably reproduce the disease in animals using it, and it didn't consistently show up where it should. The evidence was shaky, but for now, it was the only theory on the table. Meanwhile, the disease itself didn't care about any of this. It was quietly one of the deadliest recurring illnesses on the planet, devastating armies, sailors, colonists, and anyone stationed near the wrong stretch of water, especially soldiers posted far from home in the tropics. One of those postings was French colonial Algeria, where swampy garrison towns saw a relentless stream of feverish soldiers pass through the military hospitals every single season, year after year, with doctors able to treat the symptoms but never explain the cause. Posted to one of those hospitals, in the city of Constantine, was a meticulous French army doctor named Alphonse Laveran. Unconvinced by the shaky bacterium theory, he decided to do something almost nobody else had bothered to: look for himself, patiently, under his own microscope. Laveran wasn't chasing fame. He was simply, stubbornly unsatisfied with received wisdom, a trait that would define the whole story to come. If a germ caused this disease, he reasoned, someone ought to actually be able to see it, so he kept looking. Month after month, he examined blood samples from feverish patients, finding nothing conclusive. Most doctors of the era looked at blood dried and stained on a slide. Laveran, unusually, kept insisting on fresh, unstained blood, examined the moment it was drawn. What every doctor already agreed on was the disease's signature: a swollen, blackened spleen found at autopsy, and fevers that rose and fell in eerie, clockwork cycles. Everyone could describe malaria's fingerprints. Nobody could name its cause. Laveran also kept noticing something odd: strange grains of black-brown pigment scattered inside some patients' blood cells, visible under his microscope, but utterly unexplained. A small, strange detail that refused to fit anyone's existing theory. On November 6, 1880, a young feverish soldier is admitted to the Constantine hospital. Laveran draws a drop of his blood, fresh and unstained, and slides it under his microscope, the same patient habit that had turned up nothing dozens of times before. He leans in to look, and inside the red blood cells, something is moving. Not sitting still like pigment, not behaving like any bacterium he's ever studied, but writhing, alive, unmistakably in motion. Laveran freezes and looks again and again. What Laveran was watching that afternoon would take years to be believed by anyone else. But he already knew, with a certainty that would define the rest of his career, that he was looking at something no bacterium theory could ever explain. Here is exactly what Laveran saw: a small, pigmented sphere suddenly sprouting thin, whip-like filaments that lashed out violently in every direction, so forcefully that the entire red blood cell around it visibly trembled. Nothing dead does that. Nothing bacterial does that either. Laveran was instantly convinced. Whatever this was, it moved and behaved like a living, single-celled organism, not a bacterium at all, a completely different kind of culprit than the one everybody else had been chasing for the past year. He kept looking and kept finding it. The same pigmented crescent and ring-shaped forms again and again in patient after malarial patient. 26 confirmed cases showed the organism. Healthy blood, examined the same way, showed nothing like it at all. On December 24, 1880, the week of a holiday no less, Laveran sends a letter to Paris's Academy of Medicine describing his discovery, a living parasite, visible under the microscope, present specifically in the blood of malaria patients. The reaction was not celebration. It was skepticism and in some quarters outright dismissal. The scientific establishment had already settled, more or less, on the 1879 bacterium theory, and Laveran's strange, moving, pigmented organism simply didn't look like any bacterium anyone recognized. Among the doubters was the respected Italian pathologist Ettore Marchiafava, who initially rejected Laveran's claim outright. It didn't stain the way bacteria stained. It didn't grow the way bacteria grew in culture. To many trained eyes, it simply looked wrong. Rather than argue, Laveran kept doing the one thing that actually works, showing people, in person, exactly what to look for. He traveled, taught, and demonstrated his technique to visiting doctors and researchers, insisting they look at fresh blood themselves. Gradually, doctors around the world who adopted his fresh blood technique started finding the exact same organism in their own malaria patients. The evidence wasn't accumulating through argument, it was accumulating because more and more people were finally looking correctly. In 1885, two more Italian researchers, Ettore Marchiafava and Angelo Kelly, one of Laveran's earlier skeptics, now convinced, formally classify and name the organism. They call the new genus Plasmodium, the name still used for it in every biology textbook today. In 1889, nearly a decade after that first blood slide, the French Academy of Sciences awards Laveran its prestigious Brillant Prize, a formal, high-profile vindication that effectively ends the open scientific doubt about his discovery once and for all. The first half of the mystery was now closed, and it was a landmark in the history of medicine. Malaria is not bad air. It is not a bacterium. It is a living, single-celled parasite, riding invisibly inside human red blood cells. But solving what malaria was immediately opened a second equally enormous mystery. If the parasite lives only inside human blood, how does it ever escape one body and reach another? It clearly wasn't drifting through the air like a vapor. Laveran himself had a hunch. He'd never once found the parasite living freely in soil, water, or open air, only ever inside blood. That absence made him suspect some kind of biting insect might be the missing link, quietly carrying it from person to person. But a hunch wasn't proof, and Laveran had no practical way to test it. Confirming that one specific insect carried one specific parasite between specific people would take years of tedious dissection work and a very different kind of scientist to see it through. That someone was already primed for the job, thanks to an entirely different tropical disease he'd cracked years earlier. A British doctor whose own mosquito discovery would turn out to be the exact key malaria needed. His name was Patrick Manson, and years before anyone connected mosquitoes to malaria, he'd already shown that mosquitoes carry a completely different parasite, the microscopic worm that causes elephantiasis. That earlier discovery was about to change everything for malaria too. Between 1877 and 1879, working in China, Manson had proven that mosquitoes serve as an essential host for the parasitic worm that causes elephantiasis, the first time anyone had shown that a biting insect could carry a human disease agent inside it. In November 1894, Manson meets a young British doctor named Ronald Ross, visiting London on leave from India. Over dinner, Manson lays out a hunch that will consume the next several years of Ross's life. Maybe malaria leaves the body the exact same way, through a mosquito's bite. Manson formally publishes the hypothesis in the British Medical Journal on December 8, 1894. The same mosquito shown to carry the filarial worm out of human blood, he argues, may be exactly the agent that carries the malaria parasite out as well. Electrified by the idea, Ross returns to India in March 1895 as a doctor with the Indian Medical Service, determined to prove Manson's mosquito hypothesis correct, even though almost nobody else in medicine took the idea especially seriously yet. The actual work turns out to be brutally tedious. Catch mosquitoes, let them feed on malaria patients, then dissect their impossibly tiny stomachs under a microscope, over and over, hunting for any trace of Laveran's parasite hiding inside. Ross isn't a trained entomologist, so he can't even properly name the mosquito species he's studying. He invents his own private system instead, sorting them by eye into rough categories he calls gray, brindled, and dappled winged. Month after month, nothing. Wrong mosquito species, wrong feeding technique, false leads that go nowhere. Ross grows exhausted and frustrated, battling stifling heat, failing eyesight, and constant migraines, increasingly unsure whether Manson's hypothesis or his own eyesight can be trusted at all. In despairing letters home, and later in his own poetry, Ross describes moments of near total surrender, genuinely close to abandoning the search altogether, convinced the answer might simply be beyond what he was capable of finding. In June 1897, Ross transfers to a new posting in Secunderabad and switches his attention to a locally common mosquito he hasn't tried before, brown-bodied, with distinctive mottled speckled wings, one of his own dappled-winged category. To keep testing, Ross needs malaria patients willing to let his lab-raised mosquitoes feed on their infected blood. He pays a local patient, Hussein Khan, a small fee for every mosquito that successfully bites him, a modest, essential act of consent that made the whole experiment possible. After each feeding, Ross dissects mosquito after mosquito, examining their stomach walls cell by cell under the microscope. Most days end exactly the way the previous months had, with absolutely nothing to show for the effort. Then, on August 20, 1897, dissecting one of the dappled-winged mosquitoes that had fed on Hussein Khan days earlier, Ross spots something unmistakable in its stomach wall: small, round, pigmented cysts, the exact same telltale pigment Laveran had found inside human blood. This is the moment the malaria parasite, caught red-handed, actually growing inside a mosquito's gut. Manson's hunch was correct. The mosquito isn't merely present near the disease, it is the vehicle that carries it from one person to the next. Ross's own account of that day is euphoric. The next morning he writes a poem about it, one still quoted by scientists today: "I know this little thing, a myriad men will save. Ah, oh, death, where is thy sting? Thy victory, O grave." That single mosquito and that single date is honored every year as World Mosquito Day by the London School of Hygiene and Tropical Medicine. The exact anniversary of Ross's stomach wall discovery in Secunderabad, still celebrated more than a century later. But Ross's proofs so far only showed the parasite developing inside a mosquito that had already bitten a malaria patient. It didn't yet prove the mosquito could carry the parasite back OUT again into a new and healthy victim. The loop wasn't closed. To finish that final link, Ross needed to watch the entire cycle play out to completion: parasite entering, parasite maturing, parasite biting its way back out into someone new. Testing that directly on human subjects was neither practical nor remotely ethical. So Ross turns to an ingenious workaround: birds. A malaria-like parasite called proteasoma infects sparrows and crows, and he can study its entire life cycle exhaustively, in as much detail as he needs, without endangering a single human patient. Over the next year, in a makeshift aviary crowded with caged birds and mosquito netting, Ross would finally finish what a bloodslide in Constantine and a mosquito's stomach wall in Secunderabad had both started. Ross built an aviary of sparrows and crows, deliberately infects some with the bird malaria parasite, proteasoma, and lets clean, uninfected mosquitoes feed on them. The same basic experiment as before, but now with a route to the missing final step. He dissects hundreds of these gray mosquitoes, a different, more common species called culex, at every stage after feeding, tracking exactly how the parasite transforms, day by day, inside the mosquito's gut wall. Across about a week, he watches the pigmented cysts swell steadily larger, packed with countless thread-like forms crowding inside them, clearly building toward some kind of release. But toward what? And to where, exactly? On July 4, 1898, dissecting a mosquito's head, Ross finds the answer. The parasite's thread-like forms have migrated all the way up into the mosquito's salivary glands, the exact structure the mosquito uses to eject saliva during every single bite. Within days, on July 8th and 9th, Ross confirms that beyond any doubt, fully mature parasites now sit loaded in the salivary glands, primed and ready to be injected straight into the very next creature the mosquito happens to bite. Ross then lets these loaded mosquitoes bite healthy, uninfected sparrows, and days later watches the birds sicken with that exact same parasite. The full loop, start to finish, tested and proven in front of his own eyes. Ross had now done something no one had ever done for any parasitic disease before, traced its entire journey, host to mosquito, mosquito to host again, one dissected mosquito, one microscope slide at a time. He cables the results home, and the scientific world, already primed by Laveran's parasite discovery and Manson's hypothesis, receives it as the missing piece finally slotting into place, 18 years after that first bloodslide in Constantine. Meanwhile, in Italy, a separate and parallel race had been underway all along. Zoologist Giovanni Battista Grassi, working with physicians Amico Bignami and Giuseppe Bastianelli, was chasing the exact same question, but for real human malaria, not birds. Grassi had a distinct advantage. He was a trained zoologist, skilled at properly classifying insect species, and Italy, heavily burdened by malaria itself, gave his team direct access to real human patients and real malaria-carrying mosquitoes to study. By meticulously mapping exactly which mosquito species lived, where malaria thrived, and where it didn't, Grassi's team narrowed the true culprit down to one specific genus, out of dozens found across Italy: Anopheles. Through the second half of 1898, Grassi, Bignami, and Bastianelli confirmed the complete cycle directly in human malaria. Anopheles mosquitoes biting infected people, incubating the parasite inside themselves, then biting healthy people who subsequently fall ill. On December 22, 1898, Grassi formally reports the complete developmental cycle of the human malaria parasite inside Anopheles claviger, nailing down, species by species, the exact mosquito responsible for spreading malaria among people. An awkward, very human controversy follows. Both camps feel undercredited. Ross had proven the basic mosquito-to-host mechanism first, using birds. Grassi's team had proven it conclusively in humans and identified the exact vector genus involved. Historians today generally credit both fairly. Ross is the first to demonstrate the full mosquito transmission mechanism at all, and Grassi's team is the one to confirm the exact vector and completed the cycle specifically for human malaria. Whatever the credit dispute, together these two research efforts answer both halves of the question science had been chasing since Laveran's very first blood slide: what causes malaria? A plasmodium parasite, and HOW, it spreads. Anopheles mosquitoes, and only Anopheles. In 1902, Ronald Ross receives the Nobel Prize in Physiology or Medicine, honored for his work on malaria, by which he has shown how it enters the organism, becoming, remarkably, the first Nobel laureate ever born outside Europe. In 1907, Alphonse Laveran receives his own Nobel Prize, honored in recognition of his work on the role played by protozoa in causing diseases. The original discovery, finally celebrated 27 years after that first moving speck in fresh blood. Two men, working 2 decades apart on 2 different continents, had together cracked one of history's oldest, deadliest medical riddles, not through a single flash of insight, but through 2 separate discoveries, each one completing the other. With both halves finally solved, scientists could now draw the whole story as a single, continuous, closed loop. The parasite's complete journey, shuttling back and forth between 2 very different living hosts. Picture it as one continuous relay race. A mosquito's bite delivers the parasite into the liver. It erupts into the bloodstream and invades red blood cells, causing fever. Some forms are drawn up by the next mosquito's blood meal, and the cycle climbs back toward another bite. Here it is, laid out in full: the malaria parasite's complete 2-host life cycle, drawn as one closed loop, from mosquito bite to human liver to red blood cells to the next mosquito's gut to its salivary glands and back to a bite again. This map is exactly why every later weapon against malaria, bed nets, antimalarial drugs, insecticide spraying, even vaccines, could finally be aimed at one specific known point on a known loop, instead of firing blindly at imaginary bad air. 2 men, 2 decades, 2 Nobel Prizes, 1 completed loop. And now, finally armed with an actual, precise target instead of a vague, ancient curse, the real fight against malaria could genuinely begin. Knowing the vector transformed the entire strategy overnight. You no longer needed to purify the air or cure every single patient one at a time. You just needed to break the mosquitoes half of the loop, anywhere along its length. The first great real-world proof of concept came fast: the Panama Canal, 1904. An earlier French attempt to build it had partly collapsed because yellow fever and malaria together had killed roughly 1/3 of the entire workforce. American Army Dr. William Gorgas, applying this still-fresh mosquito science, launches a massive campaign, draining standing water, spreading oil on pools that couldn't be drained, screening buildings, and clearing brush. An all-out assault on mosquito breeding grounds themselves. The results are staggering. The malaria death rate among canal workers falls from 1159 per thousand in late 1906 to just 1.23 per thousand by the end of 1909, a nearly tenfold drop, and a canal that finally got built. For the next half-century, vector control becomes the standard weapon worldwide. Drain the swamp, screen the window, spray the breeding pool, attacking the mosquito directly, rather than only ever treating the fever after the fact. In 1955, the World Health Organization launches an ambitious global malaria eradication program, leaning heavily on a powerful new insecticide called DDT, sprayed onto the indoor walls where mosquitoes rest right after biting. The campaign successfully eliminates malaria across large parts of Europe, the Caribbean, and beyond, but stalls badly in the hardest-hit regions of tropical Africa. Global eradication proves far harder than hoped, and the program winds down by 1969. By the year 2000, malaria still kills roughly 864,000 people every single year, overwhelmingly young children in sub-Saharan Africa, a disease older than written history, and still, very much, an undefeated killer. Then a cheap, simple tool becomes the era's real breakthrough: the insecticide-treated bed net. In the year 2000, under 2% of the at-risk population across sub-Saharan Africa slept under 1. Within about 15 years, that climbed past half. Nets work precisely because they attack the exact weak point in Ross and Grassi's mapped loop. Anopheles mosquitoes mostly bite at night, so a simple net over a sleeping body quietly, repeatedly breaks the cycle, one prevented bite at a time. Watch the actual numbers move. Global malaria deaths fall from about 864,000 a year in 2000 toward roughly 576,000 by 2019, even as global case counts stay stubbornly near 250 million a year, as nets, drugs, and diagnosis scale up worldwide. Then, in 2020, the COVID-19 pandemic disrupts clinics and supply chains worldwide, and the decline stalls. Deaths actually tick back upward for a couple of years. A sober reminder that this fight needs constant, unglamorous maintenance, never a single final victory. By 2022, the toll still stands at roughly 249 million cases and 608,000 deaths a year. Real measurable progress compared to 2000, and still, quietly, one of the deadliest infectious diseases on the entire planet. In October 2021, the World Health Organization recommends RTS, marketed as Mosquito, the world's first ever vaccine against any parasitic disease, after pilot programs in Ghana, Kenya, and Malawi showed real drops in child deaths and severe cases. In 2023, a second, cheaper vaccine called R21 earns its own WHO recommendation. For the first time in malaria's long history, prevention no longer rests on nets and drugs alone. The human immune system itself can now be primed against the parasite directly. One more look at the loop that made all of this possible. The same mosquito to human, human to mosquito cycle that Ross and Grassi mapped in 1897 and 1898 is still the exact target every modern tool, nets, drugs, sprays, vaccines, is aimed squarely at. None of it would exist without two stubborn men chasing a question everyone else had already decided was answered. A French army doctor squinting at a moving speck in fresh blood, and a British doctor paying small change for every mosquito bite. Laveran gave the world WHHA actually is. Ross and Grassi's team gave the world how it moves. Together, they turned an ancient, faceless killer, once blamed on bad air, into a specific, targetable, genuinely beatable enemy. Malaria isn't gone. It still kills roughly a child every minute somewhere in the world. But it is no longer invisible, no longer mysterious, and no longer a curse with no explainable cause. It is a mosquito, a parasite, and a mapped loop, one that can be broken. One more look at the decline this all brought. Global malaria deaths falling from 864,000 in 2000 toward roughly 600,000 today. Cases still near 250 million. An ancient killer, cut nearly in half, and still gradually falling further. If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments which part of this surprised you the most. I read every single one. Your next story is just one click away. I'll see you there. Until next time, keep following the small, overlooked details, because sometimes the thing that's been killing people for all of recorded history turns out to be hiding inside a single drop of blood or a single mosquito's stomach wall. Stay curious.